Hello there once again. Welcome back to our Chem 152 video series. In this video, we'll talk about how to calculate the equilibrium constant K through means different from what we've discussed previously involving free energy. This question says that antimony pentachloride decomposes at 448 degrees Celsius. It gives us the reaction. Our end goal for this reaction is going to be to find its equilibrium constant. Now let's define how to calculate the equilibrium constant if we don't know the delta G standard. To find the equilibrium constant, we'll write capital K, representing the equilibrium constant, is equal to our products divided by our reactants. Now we have two options as to how we can write the K. We could write it in terms of molarity, and if we write it in terms of molarity, we'll get something called Kc, C standing for concentration. Now, since our reaction is all gases, we could write it in terms of Kp, and that will be in terms of pressure. However, if we look at the information we were given in the third line, notice that we have grams. And it's easier to go from grams to molarity than it is to go to grams to pressure. Therefore, for this question, we'll find Kc using the molarities of each of these reactants and products. Now, for part A, what we'll do is find the molarities of each of those species. Remembering that molarity is equal to moles divided by liters. So our first order of business is going to be to get moles of each of these species that are in line 3 and then divide by liters. We'll start with SbCl5. We have 3.85 grams of SbCl5. We will get out of grams and into moles, and we'll use the molar mass of SbCl5, which is 299. That will go next to grams. Then we will divide whatever answer we get by our liters. And notice our liters are given as 5 liters. So take 3.85, divide by 299, and then divide that answer by 5. You can do this in a calculator. We will get 0.002575 molarity. We will do the same thing for SbCl3. We begin with 9.14 grams of SbCl3. We will get out of grams and into moles. Using our molar mass of SbCl3, which is 228.1 grams to 1 mole, again dividing by 5. We can do this in a calculator as well. We will end up with 0.008014 molarity of SbCl3. Finally, we'll do the same thing for Cl2. Cl2 is 2.84 grams. We will get out of grams and into moles. 1 mole of Cl2 is 70.90 grams. Then we'll divide by 5.00 once again. We'll have 0.008011 molarity of Cl2. With all of our concentrations in place, now we can find the equilibrium constant. As we said previously, we'll be using Kc rather than Kp because we are operating in molarity, and we'll write the products divided by the reactants. Our products are SbCl3 multiply by Cl2 and divide by SbCl5. Be very careful to multiply your reactants and products together rather than adding or subtracting. Also, be careful about your coefficients on each reagent. If we have a coefficient next to any of the reagents, we will add that in as a power in the Kc equation. Now, in our equation that we were given, notice there were no coefficients written, so in effect, everything has a coefficient of 1, and so everything in this equation will be first power. Another thing to watch for is if you see any pure solids or pure liquids, we do not include them in the equation and just place 1 instead. However, any reagents that are aqueous or gas will appear normally. So now we know that SbCl5 goes on the bottom. We'll place that number in that position. We know SbCl3 goes to the top. Cl2 also goes to the top. And we'll place the numbers into the Kc equation. The Kc will be 0.008014 times our Cl2, which is 0.008011, divided by the SbCl5, which is 0.002575. All of these numbers are raised to the first power, so we don't have to write the exponents here. All we need to do is to do the arithmetic. We will get 0.0249 for our Kc. Notice this answer is less than 1, which means this reaction is also called endergonic. This means the reaction is not particularly favorable. For the final part of the question, we'll find the free energy change of this reaction. To find the free energy change, we can say that delta G standard equals negative RT times natural log of K. For the R, we'll use 8.314 E negative third kilojoules per mole Kelvin. For the T, we'll say that's 448 degrees Celsius. But we can't use Celsius. We'll have to add 273.15 to change to Kelvin. If we do the addition, we will end up with 721.15 Kelvin. The R will go in the first position, the temperature will go to the second position, and the K will go to the last position. So all we need to do is say that our free energy change is equal to negative 8.314 E negative third times temperature, which is 721.15, times natural log of 0.0249. We can go to a calculator to find this answer. We'll get positive 22.1 kilojoules. Meaning this reaction, as we predicted, is non-spontaneous. This means in order for this reaction to continue, we would have to add 22.1 kilojoules after starting it. Thank you for watching, and we'll see you again soon.